August 1954. Bill Harvey stands in a Berlin warehouse basement, watching a British mining engineer mark chalk lines on concrete. 450 feet to the Soviet cable junction, 18 inches of clay between the tunnel roof and a checkpoint road where Red Army boots march every morning at 0600. The Soviets installed seismic sensors every 150 feet along the sector boundary after a failed French tunnel attempt the year before. Any vibration spike means immediate raid, execution of captured engineers, loss of access to all Soviet military communications in East Berlin. Harvey needs every voice circuit on that trunk line. The engineer taps his chalk against the floor. 18 inches. Harvey briefs his team in the rented warehouse. The target is the Soviet military trunk line carrying all Red Army voice traffic in East Berlin, buried under Schoenfelder Chaussee checkpoint. Every convoy movement, every aircraft sortie, every police coordination call runs through that cable. British SIS assigns a mining engineer who worked UK coal pits. He unrolls soil survey maps showing the shallowest point, 18 inches of clay between planned tunnel roof and road surface, right where Soviet foot patrols cross twice per hour. Harvey explains the constraint. Soviets installed seismic sensors every 150 feet along the sector boundary after the 1953 French tunnel attempt. Sensors trigger at vibration thresholds typical of excavation equipment. Sustained low-frequency rumble, not the short spikes from truck traffic. The warehouse sits 450 feet from the cable. The crew must dig horizontally under the American sector, cross beneath the boundary road undetected, and build a tap chamber on the Soviet side. One 10-second burst of metal scraping is enough to trigger investigation. Standard tunnel boring generates 60 decibels of metal scraping. Through clay soil, that sound carries up to 200 feet, well within Soviet listening post range. The engineer selects a circular steel shield with a hydraulic faceplate. Normally it scrapes forward, steel teeth biting clay. He proposes a modification. Pack the annular gap with sandbags to dampen vibration before it reaches soil, and replace the cutting teeth with rubberized pads. The question is whether 40% less hydraulic pressure will still advance the shield without stalling in dense clay. Clay soil conducts vibration efficiently. Compressive waves travel at roughly 1,000 feet per second, so any metal-on-metal impact in the tunnel face reaches the road surface in less than half a second. Soviet seismic sensors are calibrated to distinguish truck traffic, short-duration spikes, from excavation, which produces sustained, low-frequency rumble. The sensors sit in sealed housings buried 3 feet below the road, continuously feeding data to a monitoring station in the East Berlin signals complex. Detection margin is tight. The crew tests the shield in a practice pit under the warehouse. Normal hydraulic advance generates 58 decibels at the face. A microphone buried 18 inches above the tunnel roof registers 34 decibels, above the 30 decibel ambient threshold that Soviet sensors use to filter truck noise from excavation signatures. The test fails. The engineer orders a retrofit. Replace steel cutting teeth with rubberized pads, reduce hydraulic pressure by 40%, and hand excavate the final 2 inches of each advance to eliminate all metal contact with clay. Second problem. 30 men working 8-hour shifts in a sealed 6-foot diameter tunnel produce 4,200 cubic feet of carbon dioxide-enriched exhaust per hour, 15 degrees warmer than surface air. Soviet infrared aerial reconnaissance flies over the American sector every 72 hours, looking for heat signatures that match underground activity patterns. A visible thermal plume rising from the warehouse would correlate with the cable route and trigger investigation. The CIA facility engineer installs a ventilation system disguised as warehouse heating. The exhaust is mixed with cold air in a plenum chamber before release, and the stack is baffled to disperse the thermal plume below infrared detection resolution. The facility engineer calculates the mixing ratio needed to drop exhaust temperature to within 2 degrees of ambient, enough to blend with normal warehouse heating signatures. Baffles spread the plume across a 40-foot rooftop area, instead of a single concentrated vent. Soviet reconnaissance aircraft would need to detect a 2-degree anomaly across that dispersed area, below the threshold of 1950's infrared camera sensitivity. February 1955. The tunnel advances at 18 inches per 8-hour shift. The modified shield moves in 5-minute increments. Hydraulic push, sandbag packing around the steel collar. Then 2 men hand excavate the final 2 inches of clay before the next push. No metal touches soil. The rubberized pads compress clay without scraping. A contact microphone mounted on the shield frame monitors vibration in real time. If it spikes above 28 decibels, the crew stops and waits for the reading to settle before resuming. At 380 feet, the crew passes directly under the checkpoint road. The engineer places a contact microphone against the tunnel roof and hears boot strikes and truck axles 6 feet overhead. 18 inches of clay dampening the sound to a muffled thud. Soviet foot patrols cross twice per hour. Each time, the crew freezes until the boots pass. No seismic alarms. The Soviets continue routine patrol, unaware that 30 American and British engineers are working 6 feet below their boots. Harvey authorizes the final 70-foot push into East Berlin soil. May 1955. The tunnel reaches the cable location. The crew digs a vertical shaft and exposes the trunk line. 1.2 inches of lead sheathing over 432 individual copper pairs bundled inside. No external markings indicate where each wire sits within the sheath. The cable is cold to the touch, live, with 19,000 volts. A Bell Labs Wiretap specialist arrives from Washington carrying a crate of induction coils, toroids designed to detect magnetic flux from voice current without cutting insulation, but only if placed within 0.4 inches of the copper core beneath the lead. Cutting the lead to find wire positions would create a voltage drop. The Soviet cable carries 432 voice circuits at 19,000 volts, and any insulation breach triggers alarms at both trunk ends within 0.3 seconds, dispatching armed technicians to the site within 8 minutes. The specialist instead uses a Gauss meter to map magnetic field strength across the cable surface, hunting for flux peaks that indicate copper location beneath the sheath. First sweep shows noise. 432 circuits create overlapping magnetic fields that blur into crosstalk static. The specialist realizes he needs to map during a known test signal. Isolate one wire carrying a call at a known time, then correlate that moment with a coil output spike. But Soviet cable maintenance schedules are classified, and the trunk line carries hundreds of simultaneous conversations during peak hours. He briefs Harvey on the problem. Harvey sees the solution. Wait for a predictable event that triggers a specific call from East Berlin headquarters. Then record all 432 coil outputs simultaneously and use differential analysis to identify which coil captures that call. Voice current in a copper wire generates a circular magnetic field. Field strength drops with the inverse square of distance. At 0.4 inches, a coil picks up clear signal. At 0.8 inches, the signal is buried in crosstalk from adjacent wires. The Soviet cable uses lead sheathing as both moisture barrier and electromagnetic shield. Lead attenuates high-frequency noise, but passes the 300 to 3400 Hz voice band, meaning the coils can work through it if positioned precisely. Each of the 432 wire pairs sits in a twisted bundle. Twisting cancels some self-generated flux, so the coils must encircle the wire axis, not just sit adjacent. Toroid geometry required. The specialist fabricates 432 small toroids, each 2 inches in diameter, wound with copper wire. He mounts them on a flexible rubber mat that wraps around the cable like a sleeve. Now he needs to map which toroid aligns with which wire inside the sheath. The mat holds all coils in fixed position, and each coil feeds into a numbered amphenol connector, so outputs can be recorded separately. The challenge is correlating coil number with the invisible wire beneath it. No X-ray, no visual reference, only magnetic field data during live voice traffic. Harvey arranges for a U.S. Army spotter in West Berlin to note the exact time a Soviet convoy crosses the checkpoint, triggering a radio call from East Berlin headquarters to the convoy. When the call happens, the specialist records all 432 coil outputs simultaneously on a 24-track reel-to-reel system. Differential analysis shows one coil spiking at the known call time. That coil is now mapped to the headquarters trunk line. Over 3 weeks, the team maps 172 high-priority circuits by correlating coil output with observed Soviet activity, convoy movements, shift changes, aircraft departures at Schoenfeld Airfield. Remaining circuits are mapped by cross-referencing call time patterns. The team logs all 432 channels for 48 hours. Then, analysts in the warehouse study the recordings to identify recurring call patterns: morning roll calls, hourly maintenance reports, evening shift handovers. Once a pattern is established, the corresponding coil is tagged with its circuit function. By July 1955, all coils are aligned and feeding into shielded cable that runs back through the tunnel to the warehouse, where reel-to-reel recorders capture 24-track audio around the clock. October 1955. Berlin receives 2.4 inches of rain in 36 hours. Clay soil absorbs water and expands volumetrically, pushing upward against the tunnel roof with hydrostatic pressure. The engineer monitors the tap chamber with a laser level and sees the ceiling rise 1/4 inch per hour. At this rate, the tunnel will contact the road base layer in 18 hours, creating a surface depression visible to Soviet patrols. Harvey faces a choice: shut down the recorders and possibly collapse the tunnel to hide evidence, or keep recording and risk discovery. Harvey orders the recorders left running. Intelligence yield is critical, and shutting down means abandoning the tap chamber and possibly losing access forever. The crew installs hydraulic jacks between tunnel floor and roof in the tap chamber, transferring ceiling load downward into the clay below. Jacks are pressurized slowly, raising pressure by 10 pounds per square inch every 30 minutes to avoid sudden soil displacement that would register on seismic sensors. Each jack supports roughly 800 pounds of ceiling load, spread across 4 contact points. Rain stops after 48 hours. Soil drainage begins, and the ceiling settles back to baseline over 4 days. The jacks hold position until expansion fully reverses, then are slowly depressurized at the same 10 pounds per 30 minutes rate to avoid rebound shock. No surface depression appears. Soviet patrols continue routine, unaware of the crisis 6 feet below their boots. Harvey logs the event as a near miss and briefs CIA engineering on soil hydrology risks for future tunnel operations. The recorders never stopped. The tunnel records continuously from August 1955 to April 21, 1956. 443 days, capturing Soviet military voice traffic, including troop movements, aircraft maintenance logs, and East German police coordination. The warehouse recorders fill more than 40,000 hours of reel-to-reel tape, shipped in weekly batches to CIA headquarters in Washington for transcription and analysis. Analysts identify Soviet order of battle data for East Germany, track the movement of armored divisions, and log the radio call signs of Red Army air defense units stationed around Berlin. April 22, 1956. A Soviet cable maintenance crew digs at the tap chamber location and discovers the tunnel. Within hours, Soviet officials hold a press conference and invite Western journalists to tour the site, framing it as evidence of American espionage. Journalists photograph the tunnel, the coil array still wrapped around the cable, and the warehouse basement entrance. The Soviets label it a violation of the Berlin Agreement and a provocation against East German sovereignty. The U.S. officially denies involvement. CIA evacuates the warehouse and destroys records linking personnel to the operation. The recordings are flown to Washington and archived for analysis. CIA signals intelligence analysts spend the next 2 years transcribing calls, correlating voices with known Soviet officers, and building a database of Red Army communication protocols. The tapes reveal Soviet concerns about NATO tactical nuclear deployments, internal debates over resource allocation between armored and air defense units, and the names of KGB officers coordinating surveillance in West Berlin. Despite the tunnel's exposure, the intelligence remains actionable because the Soviets do not know which circuits were tapped or which calls were recorded. 1961. George Blake, a British SIS liaison officer who attended planning meetings in 1953, is arrested as a KGB mole. He confesses to briefing the Soviets before the tunnel was dug. Declassified KGB files later reveal the Soviets knew about Operation Gold from the start, but allowed it to continue. Their reasoning? Shutting it down immediately would burn Blake, and letting it run gave them a chance to study U.S. intercept technology and feed selected disinformation through the tapped lines. The Soviets calculated that the intelligence risk was acceptable if it protected their source and let them map American signals intelligence capabilities. Despite the compromise, intelligence assessment concludes the recordings provided actionable data on Soviet order of battle in East Germany and validated new non-invasive wiretap methods. The induction coil technique, refined under Operation Gold, became standard for NSA operations in the 1960s. The lesson: even when adversaries know about the operation, the specific content captured can remain valuable if they cannot determine which circuits or calls were intercepted. The Soviets faced a dilemma. Altering all voice traffic protocols would signal awareness and burn Blake, so they allowed normal operations to continue on most circuits. The Berlin Tunnel established Doctrine for covert signals intelligence infrastructure. Silent digging techniques, induction coil tapping, and thermal signature management became template requirements for Cold War tunnel projects in Vienna, Saigon, and the demilitarized zone in Korea. Harvey's operational security protocols, compartmentalized crews, cover facility engineering, seismic monitoring, are still taught in CIA training as case studies in technical intelligence tradecraft. The 450-foot tunnel remained the longest covert signals intelligence excavation until the 1970s, and the engineering methods developed under Operation Gold influenced a generation of underground intercept operations. The sensors can distinguish a truck passing in 4 seconds from excavation that rumbles for minutes. Every 5-minute shield advance must stay below that detection signature, meaning the hydraulic push phase is limited to 90 seconds, followed by silent sandbag packing and hand excavation. The crew operates on a stopwatch. Push begins at the top of each 5-minute cycle. Hydraulics shut off at 90 seconds, and no metal tool touches clay for the remaining 210 seconds. One missed timing means detection. The facility engineer calculates the cold air mixing ratio using basic thermodynamics. 4,200 cubic feet of 85-degree exhaust must be diluted with enough 70-degree ambient air to reach 72 degrees at the stack outlet. The ratio works out to roughly 4 parts cold air to 1 part tunnel exhaust. A fan array in the plenum chamber pulls warehouse air through ducts and blends it before venting. The system consumes 18 kilowatts of electrical power continuously, disguised as heating load on the warehouse utility bills. Any reduction in mixing airflow would create a detectable thermal plume. The specialist wraps the coil mat around the cable and powers up the recording system. First test reveals the crosstalk problem. Hundreds of overlapping voice frequencies create a noise floor that buries individual circuits. He realizes the 432 wires are not evenly spaced inside the sheath. Some bundles sit closer to the surface, generating stronger fields, while others are deeper and produce weaker signals. Without a map correlating coil position to wire depth, the recordings are useless. He needs a way to isolate individual circuits during live traffic, which brings him back to the known signal mapping strategy. The toroid design is critical. A flat coil placed adjacent to the wire picks up flux from neighboring wires because the field spreads in all directions. A toroid encircles the wire axis, so it captures flux only from the wire passing through its center, rejecting off-axis interference. Each toroid is wound with 200 turns of copper wire, creating enough inductance to generate a measurable voltage from the weak magnetic field passing through 1.2 inches of lead. The specialist tests coil sensitivity by passing a known current through a wire inside a lead sleeve. Output voltage matches the calculated value, confirming the design will work on the live cable. When the convoy call happens, all 432 coils are recording. The specialist loads the tapes into a differential analyzer. a bank of 24 playback heads feeding into a comparator circuit. He sets the known call time as a reference marker and scans all channels for amplitude spikes within a 2-second window. One coil shows a 12 decibel spike at the exact moment. That coil is tagged as headquarters trunk line circuit. The remaining coils show only ambient noise at that timestamp. The process is repeated for each observed event: shift change calls, aircraft departure clearances, police dispatch orders. Each event adds another mapped coil to the database. The engineer sets up 3 laser levels at 50-foot intervals along the tunnel, each projecting a reference line onto the ceiling. Every 2 hours, a crew member measures the distance from laser line to ceiling with a micrometer caliper, logging the value on a waterproof chart. The first measurement after rain starts shows baseline. 6 hours later, the ceiling has risen 1/8 inch at the shallowest point under the checkpoint road. By 12 hours, it is up 1/4 inch. The chart projects contact with the road base layer in 18 hours if the rise continues at the current rate. The data drives Harvey's decision to install jacks rather than evacuate. Each jack must support roughly 800 pounds of ceiling load without creating pressure spikes in the surrounding clay. The crew places jacks on steel base plates to distribute load over a wider soil area, reducing point pressure. Hydraulic lines are connected to a central pump with a pressure gauge calibrated in 10-pound increments. The engineer calculates that pressurizing too quickly, more than 10 pounds per square inch every 30 minutes, will displace clay upward into the road base, creating the exact surface depression they are trying to prevent. Slow pressurization allows clay to compress gradually and absorb the load without visible displacement. As soil drains, the crew continues ceiling measurements every 2 hours. The rise peaks at 3/8 inch, then stabilizes for 12 hours before beginning to drop. By day 2, the ceiling is down to 1/4 inch above baseline. Day 3 shows 1/8 inch. Day 4 returns to baseline. Throughout this period, the jacks hold constant pressure, and the recorders never stop. Soviet patrols pass overhead on schedule, and infrared reconnaissance flights detect no anomaly. Harvey's gamble paid off. The tunnel remained hidden because the engineering countermeasure worked exactly as calculated, and the operational priority never wavered. At CIA headquarters, transcription teams work in shifts, each analyst assigned a single circuit. Native Russian speakers translate conversations in real time, flagging keywords, division names, officer ranks, equipment types, grid coordinates. A second team cross-references flagged items against existing intelligence files to identify speakers and locations. A third team builds network diagrams showing communication patterns between units. The workflow turns 40,000 hours of audio into a structured database of Soviet order of battle, revealing which divisions are under strength, which airfields lack spare parts, and which officers are being considered for promotion or reassignment. KGB counterintelligence faced a dilemma when Blake briefed them in 1953. Shutting down the tunnel immediately would signal that they had a mole in British SIS, risking Blake's exposure and the loss of future intelligence. Letting it run allowed them to study American induction coil technology, identify which circuits the US prioritized, and feed carefully crafted disinformation through selected lines. The KGB calculated that protecting Blake was worth the intelligence loss, and that mapping US signals intelligence methods would pay dividends in future operations. The April 1956 discovery was staged as routine maintenance to avoid revealing Blake's role. Before Operation Gold, signals intelligence required physically cutting into cables to attach taps, which created detectable voltage drops and required repair teams to hide the intrusion. The induction coil method validated in Berlin eliminated that risk entirely. No cut, no voltage drop, no alarm. NSA adopted the technique as standard doctrine by 1958, and it became the foundation for underwater cable taps deployed on Soviet submarine communication lines in the 1970s. The principle remained the same. Encircle the conductor with a toroid, measure the magnetic flux, and record the induced voltage without ever touching the wire itself. The modified shield technique, rubberized pads, reduced hydraulic pressure, Incremental advance with hand excavation became the template for subsequent Cold War tunnel projects. In Vienna, CIA dug under a Soviet signals facility using the same 5-minute cycle timing and sandbag damping method. In Korea, a tunnel under the DMZ employed hydraulic jacks during monsoon season to counter soil expansion, directly applying the lessons from Berlin's October 1955 rain event. Each operation refined the doctrine further, but the core principle remained. Vibration control and incremental advance are non-negotiable when digging within detection range of adversary sensors. Harvey compartmentalized the operation into isolated cells. Digging crew, wiretap specialists, ventilation engineers, and analysts never met or knew each other's names. Cover facility engineering was detailed enough that warehouse utility bills, employee rosters, and truck delivery schedules matched the profile of a legitimate logistics depot. Seismic monitoring was continuous, with sensors in the tunnel feeding data to a control room where any vibration spike above 28 decibels triggered an immediate work stoppage. These protocols are still taught in CIA training as case studies in technical intelligence tradecraft, illustrating how operational security and engineering discipline must integrate seamlessly. The 450-foot Berlin Tunnel remained the longest covert signals intelligence excavation until the 1970s, when longer tunnels were dug under the demilitarized zone in Korea and under Soviet communication facilities in Afghanistan. The engineering methods developed under Operation Gold, silent shield operation, non-invasive cable tapping, thermal signature management, and soil hydrology risk assessment influenced a generation of underground intercept operations. The tunnel itself was sealed by the Soviets after discovery, but segments of the tap chamber and coil array were later recovered and are now displayed at the Allied Museum in Berlin as artifacts of Cold War technical intelligence. The 18-inch margin between tunnel roof and Soviet boots became a symbol of Cold War engineering discipline, the absolute minimum separation that silent excavation techniques could maintain under seismic detection constraints. That margin demanded every countermeasure Harvey's team deployed: rubberized shield pads, incremental advance timing, hydraulic jacks during rain, thermal exhaust mixing, and non-invasive induction coil tapping. The operation proved that technical intelligence could succeed even when adversaries knew about it, as long as engineering precision and operational security remained airtight. 18 inches was enough because the engineers made it enough.